Yes, I am. Great. Thank you, Tristan. So yeah, our first session, as Tristan so nicely put out, is going to focus on the first of those three things that Tristan was talking about there, three parts of the puzzle, as he said. So this first session is going to look at what we've learned from COVID. So the role that schools play in community transmission. So I'd like to welcome our first speaker, James Munday from the London School of Hygiene and Tropical Medicine, SHTM. So James, I believe, is going to talk to us about work looking at using community data to evaluate the potential wider impact of school-based SARS-CoV-2 transmission. So lessons that we've learned and reflections on that. And yeah, if people have questions, as Jane said at the beginning, feel free to put those in the chat or raise a hand at the end, and I think we'll take all questions at the end of the talk. So with that, I'll pass over to you, James.
Thank you so much, Kira, and thank you, Tristan and Jane, as well, for organising this event. I think it's a really important topic and great to see a really broad approach to it, and also such a pleasure to speak alongside such distinguished colleagues. So thank you for inviting me. I wanted to present some reflections on some work that we did earlier in the pandemic, on using kind of data-driven approaches to understand particularly the impact of reopening schools after lockdown. So that's the context of the work, but obviously it kind of pertains to the potential impact of transmission within schools, and then the kind of particularly the impact on the community as that transmission occurs. So first of all, I'll kind of open with discussing what I mean by community data, and how I'm tying those together. And then I'm going to present two pieces of work that we did. The first, using school census data to evaluate the wider implications of school transmission. And then secondly, some work we did using social contact data. And then I'll tie up the talk by considering kind of thoughts on use of community data in this context, and whether these were successful and what we might want to change in the future. So community data, I mean, by community data, I'm using kind of a broad definition for data sources that don't directly detail epidemiological phenomenon, but they may be used as a proxy to evaluate the potential risk of transmission in certain scenarios. So we used two key community data sets. The first is school census data, which is pupil level data for every state school in England, which we got from with permission from the Department for Education. And then secondly, social contact data, which is essentially social contacts of participants collected, in this case, using a regular contact survey of the UK population. But other examples of community data may be mobility data, which detail geographical movement of individuals in the population, or, for example, time use data, which is generally generated from surveys similar to, I guess, to contact surveys, but looking at more how time's spent. So these data sources don't directly pertain to transmission, unlike, for example, contact tracing data, but we're using them to essentially as a proxy to look at the impact of transmission in schools. So just quickly, a reminder of what the kind of timeline of the pandemic looked like in England. So there were three kind of national lockdown periods. The first starting in March 2020, the second in November, and the third in the new year in 2021. And during the kind of, over this period, there were also enforced school closures, and these broadly aligned with the national lockdown periods 1 and 3, whereas in lockdown 2, there were no the schools remained open, whereas the rest of the population was restricted to stay-at-home orders. So the first piece of work I'm going to present, we used the National Schools Census data to evaluate the implications of reopening. And we did that at the kind of the end of lockdown 1. So as schools reopened for the first time after they were closed in March 2020, And we wanted to look at the potential for large-scale transmission facilitated by schools. So rather than just within school transmission, what would happen if we assume that transmission is going to occur? And we compared various reopening scenarios. So reopening primary schools, reopening secondary schools, all schools, and also scenario reopening just the transition years of schools. And we looked at a range of different within school reproduction numbers between 1.1 and 1.5. So school census data, which was provided to us from the Department of England, Department for Education, includes just over 21,000 state-funded schools in England, and details just under 5 million primary school children, and 3.5 million, well, around about 3.5 million secondary school children, and they live in kind of collectively in about 5 million unique addresses. And so this is key. So there's kind of obviously some overlap with where these children live, and that's the point. That's how we what we wanted to kind of take advantage of. So if you consider a human population as a network, maybe the most natural communities to define in the population are households, typically, because they form cliques. We expect everyone in the household to have contact with each other, and then these households are linked together by contacts outside in the community. But we're specifically interested in school contacts. So it becomes convenient to consider the network, rather than a network of households with 5 million nodes, a network of schools with 21,000 nodes in this case, where household contacts are then incorporated in the edges between the schools, the links between the schools. So by identifying groups of students that share households using postcodes, we're able to build a network of schools based on likely contact links through those households. And then the edges in this kind of first network here, with the purple network, are the number of unique contact pairs between schools based on the household data we have. So then using that network, we can estimate the probability of transmission between schools by making some simple assumptions about final size of outbreaks in schools and transmission within the home. And so that network B gives us a probability of transmission between schools on each edge. And then thirdly, by sampling these probabilities, we can create binary outbreak networks, which are essentially plane networks with kind of binary edges. And these simulated networks give us some information about the final size distribution of outbreaks that we'd expect by taking the connected components. So the largest component here, shown with kind of highlighted in blue, gives the largest outbreak on that network, the number of schools you'd expect to be infected in that outbreak. So first, looking at kind of the contact network degree distributions, the degree gives the number of schools connected on the network, but the weighted degree gives the number of contacts with other schools. So in this plot, you can see these kind of degree distributions with primary schools in blue and secondary schools in red. And you can immediately see that both the degree and weighted degree are higher for secondary schools than primary schools. So this may be partly due to secondary schools being larger, but we also saw evidence that within households, it's more likely that multiple secondary schools are represented than multiple primary schools. So this may play a part in that. Similarly, we look at the weighted degree of the transmission network. So the weighted degree of a school A, so kind of a particular school A, gives the expected number of neighboring schools where outbreaks might be seeded in the event that an outbreak in school A. So it's the sum of the probabilities gives the kind of expected number of seeded outbreaks. So again, secondary schools here in panel C result in a higher average number of seeded outbreaks than primary schools, and which are very similar to kind of the select school years, the transition years. And then reopening all years is higher again. And another thing to note is this kind of very fat tail on these distributions, which indicates that there's potential for kind of schools that could seed a very large number of outbreaks. So kind of almost super spreading schools within the network if you have outbreaks in those schools. So this suggests that potentially secondary schools, on average, if you have an outbreak in secondary schools, you're more likely to see rapid spread into the kind of local area than within primary schools. And then looking at these kind of outbreak size distributions, using the connected components on the simulated binary outbreak networks. Again, the first two panels show the transition years and reopening primary schools, and for the most part, the final sizes are small, so between kind of 1 and 600 households in this case. I've translated this back to households. This is the number of households in schools affected, not necessarily the number of households with infections. So you have kind of, between 100 and 600 households affected, but reopening secondary schools allows the network to connect up much more easily, and as a result you get these very, very large outbreaks occurring, up to kind of 2.5 million households affected, which is a large proportion of households represented in secondary schools. And then reopening all schools, obviously adding more connections in the network, allows an even larger number of households to be connected. Obviously, you would hope that interventions would other interventions may stop this, but this is kind of like the final size that you might expect if nothing was done, according to this framework. So there are some really key limitations to this work. First of all, it neglects any transmission outside the household, outside of school and household populations. It relies on supercritical transmission in schools, which wasn't necessarily clear, I guess, early on in the pandemic, but potentially is more clear now, especially with recent variants. It ignores internal school structure, for example, classes and year groups, which may affect the kind of final size of outbreaks. It assumes transmission potential is equal in all schools, and importantly, that immunity doesn't vary by age or geography, which might be important, as immunity is gained from infection differently in different geographical locations. So it's kind of, limited. But I wanted to kind of now reflect on kind of this use. We did it quickly as a kind of in a kind of response framework. And so was this useful? Is it useful? And when could it be applied? So I think it provides a useful insight into the far-reaching potential of transmission within schools in any context, and particularly highlights the difference between primary and secondary schools when it comes to wider transmission and how connected they are on these networks. In the context of the pandemic, there aren't many scenarios where the simplifications we made apply directly. There were a few points in the pandemic when they were more applicable. For example, lockdown 2, as I mentioned, where the adult population was largely locked down, but the schools were closed. No, so schools were open, and then kind of more recently, as the adult population immunity increased with vaccination, but children mostly remained unvaccinated. And then also it's potentially more applicable in scenarios where schools are highly influential in transmission, like, for example, we know for influenza, and maybe for COVID-19 in the future, depending on how it progresses. So for the second piece of work I want to present, we used contact data to evaluate the potential of reopening, potential increase in transmission from reopening schools in March 2021. So this is kind of in the middle of the third lockdown. And the contact data we used it was collected as part of the COMIX survey, which is a large contact survey that's conducted in a total of 17 countries, but we use the UK data. The data includes contacts from the previous 24 hours of each participant, and details of the contact events, including the age, location, duration of contact, and whether contacts were physical or conversational. There's actually a load of other information in there which we're not really using as well. In the UK, there are about 2,500 adults enrolled, 500 children. Data was collected weekly, and there are around 100 rounds of the survey, taking you from kind of March 2020 to February 2022. So it's a big data set, but helpfully, we've got this kind of time varying contact data, so we can look back at the rest of the pandemic and kind of use that data from different periods to understand how the interventions affected contacts. So one really neat thing about contact data is you can construct contact matrices, which effectively give the mean number of contacts between age groups. And these can directly inform kind of epidemiological parameters or give us information about epidemiological parameters via the next generation principle, which is essentially, so the next generation matrix is defined. So if you multiply the age stratified infections at generation G by the next generation matrix, you get age stratified infections at generation G+1. And the next generation matrix is essentially an augmentation of the contact matrix by the age-specific susceptibility and age-specific infectiousness. So a key property of the next generation matrix is at transmission equilibrium, the age-stratified infectiousness becomes, or distribution of infectiousness becomes an eigenvector whose eigenvalues are naught. So the eigenvalue of the next generation matrix is the basic reproduction number. So we're using this property to kind of link the contact data to transmission in the population. So what we kind of did was we took advantage of the fact that schools were open during lockdown 2, but weren't open during lockdown 3. And we combined these data to kind of evaluate what the impact of, based on the current reproduction number, what the impact might be as schools reopened under 3 scenarios. So firstly, all schools open and primary schools open and secondary schools open. So for each scenario, we have a scenario contact matrix. For all schools open, we just used the lockdown 2 matrix. So that's where we assume that it's going to move back to something like what we observed in lockdown 2. And then for primary schools open and secondary schools open, we modified the matrices. So for primary schools open, we basically installed the lockdown 3 contacts of secondary school children because they remain closed. For secondary schools open, we installed the lockdown 3 contacts for primary school children. So we can kind of combine these 2 matrices to make these scenario matrices. And by taking the eigenvalue of the contact matrix, which is then augmented by an age-specific infectiousness and susceptibility, these are relative vectors now. They don't, because we're taking the ratio, we can do that. So we take the eigenvalue of essentially that kind of pseudo next generation matrix and that which we're observing in lockdown 3. And that gives us the relative increase in reproduction number that we'd expect as schools reopen. And what did we find? Well, we found that depending on the assumptions regarding age-specific susceptibility and infectiousness, which we took from different published work, and we also used the COMICS data to try and estimate ourselves, we estimated an increase between kind of 1.3 and 1.6 times the reopening times increase as we reopen schools. So this is 1.3 to 1.6 times the pre-opening reproduction number value. Obviously, there are some key limitations to this work as well. We assume that all contacts are the same, critically within schools and outside of schools. We assume that changes in R are immediate, but actually, when you change kind of the distribution of contacts by age rapidly, then you expect kind of a bedding in period where you reach equilibrium, which can take a few generations of infection. We assume that the age distribution of immunity captured was in the estimates. The age distribution of immunity is captured in the estimates of age-specific susceptibility. So some of these estimates were quite old, and actually, as infections as we get more infections in different age groups, that might change. We assume the infectiousness and susceptibility of all children is equal. So primary schools and secondary schools, school children have equal susceptibility and infectiousness. And we assume that both child and adult contacts reverted to the same as what we observed in lockdown 2 if schools reopened. But this is important, because we knew there were some changes actually within school, in terms of within school contacts. Within school restrictions which may affect contacts, but we weren't able to implement those. So if we look at how we can actually kind of check how this went in terms of comparing to the estimates of R that followed. So R did increase, but not initially as much as we anticipated. You can see the national R estimates. These are the UK national R estimates from the government website, weekly, in these kind of grey blocks, and then the purple and blue panes here show the two of the scenarios using different infectiousness and susceptibility estimates that we used. So you can see we're kind of over predicting, but there were many other factors affecting reproduction number at the time. So it's actually quite difficult to know, kind of to really disentangle this from our framework. So I mentioned new school measures. There's also this school holiday, which occurred 3 weeks after schools reopened. These are estimates are slightly delayed. So you'd expect kind of a week or two delay in seeing the change. There were also the green lines here show the removal of other restrictions as kind of lockdown was lifted. And then right at the end here, we're kind of starting to see the emergence of Delta, which is likely to drastically increase R itself. So I think in terms of use and applicability, I think it provides at the time it provided a rough estimate of the potential additional contribution of schools using the data that was available. It's really difficult to quantify how well that worked. But I think it does highlight like the importance of understanding these kind of contact data a bit better, especially kind of the nuances of different contacts in different locations. So just to sum up overall, I think these kind of data-driven approaches give a really, their key benefit is that they give like a very transparent metric, in the sense that they allow structured assessment of particular transmission phenomena without combining the kind of data with other modeling assumptions. So it's clear where the limitations lie. This kind of comes with some problems though. For example, they really require clear communication, because the results are likely to be quite abstract, and more abstract than traditional modeling results, which may not pertain directly to kind of the reality that you expect. And then thirdly, there's a key downside is it's difficult sometimes to integrate even known additional complications, as it's difficult, as you can't kind of incorporate them without applying judgments of your own in how that might affect the framework. For example, transmission outside schools in the first piece of work, and additional control measures in the second. So I just want to thank my co-authors, of which there are many, the Department for Education for providing the school data, COMIX survey team, and also some Juniper colleagues who were really helpful with the contact work in March.
Great, thank you very much, James. I'll give you a virtual clap, as we're not in the INO itself. That was really interesting. While people are thinking of questions to put in the chat, we've got a few minutes if people want to ask any quick questions. I had a quick question. It's a slightly it's about sort of how you implement the impacts of school closures for lockdown 1 and lockdown 3, and apologies if you mentioned it and I didn't understand, but because obviously although schools were closed, they remained open